So far, the circuits that we have considered include batteries or generators that contribute only their EMFs to a circuit. In reality, however, such devices also add some resistance. This resistance is called the internal resistance of the battery or generator because it is located inside the device. In a battery, the internal resistance is due to the chemicals within the battery. In a generator, the internal resistance is the resistance of the wires or other components within the generator. Here we show a schematic representation that represents the internal resistance R of a battery. As seen in the schematic, when an external resistance is connected to the battery, the resistance is connected in series with the internal resistance. The internal resistance of a functioning battery is typically small, several thousandths of an ohm for a new car battery. Nevertheless, the effect of the internal resistance may not be negligible. Here we show a simple example that illustrates that when a current is drawn from a battery, the internal resistance causes the voltage between the terminals to drop below the maximum value specified by the battery's EMF. The actual voltage between the terminals of a battery is known as the terminal voltage. Consider a typical Type D dry cell flashlight battery that, when new, can maintain a voltage difference of 1.50 volts across its terminals, close to its ideal EMF. After it ages, its internal resistance grows to R equals 0.090 ohms. By how much has its terminal voltage decreased if you assume it supplies a current of 1.10 amps through some device connected across its terminals? The voltage between the terminals is not the entire 1.50 volts EMF, because part of the EMF is needed to make the current go through the internal resistance. The amount of voltage needed can be determined from Ohm's law as the current I through the battery times the internal resistance R. For larger currents, a larger amount of voltage is needed, leaving less of the EMF between the terminals. The drop in voltage we'll call VR and is given by VR equals IR equals 1.10 amps times 0.90 ohms, which equals 0.10 volts. Therefore, the actual voltage across the battery terminals with this current is 1.50 volts minus 0.10 volts, which equals 1.40 volts. Therefore, 1.40 volts is the terminal voltage under these conditions. Note that, since the voltage drop across the internal resistance, VR equals IR, is proportional to the current, the terminal voltage decreases for larger currents. In summary, all real batteries and generators have an internal resistance. Next, the internal resistance is in series with whatever device is connected across the battery or generator terminals. Finally, the terminal voltage is the actual voltage across the terminals of the battery or generator, meaning that the internal resistance is taken into account. This means that the terminal voltage is always less than the ideal EMF.